Okay, I'm going to tell you a little bit about a program we have to look for white dwarfs with infrared excesses in a globular star cluster with JWST. Don't get your hopes up for a final result about this. This is an early results. We do have the data. They're being processed as we speak, but there are some issues with the data that have to be sorted out. But I will give you a sense of what we're doing and how it's going. So there's a big motivation here if you want to talk about a background. When did the universe, when was it first capable of supporting life? And I don't know the answer to that, but presumably it was preceded by the formation of the first planet. So when did this occur? Well, there's been a little bit of work on this. For example, there was a planetary transit program 20 years ago or so, or 15 years ago, with Hubble in the same cluster I'm going to be talking about, 47 Tucani, age about 10 gigayears, and they looked for planetary transits. It wasn't a very sensitive survey because they only could look for hot Jupiters at the time, and no evidence of planets were found. We know that Messier 4, another globular cluster, quite metal poor, has a planet, but the planet's in orbit around a neutron star, so it's not at all clear what the origin of that planet is. So in this program, we decided to look for evidence of debris in a globular cluster around white dwarfs by examining the white dwarfs for an infrared excess. So here's some work we did, which is critical background work because we couldn't do this unless we had this information. So these are some very deep HST color magnitude diagrams of 47 Tucani, which we've been working on more or less for the last 20 years. Here's the main sequence of the cluster. This is the white dwarf cooling sequence of the cluster. And this is the SMC, which sits in the background. But with 7, 8, 9 years of time, you can actually reasonably well get rid of the entire SMC by doing proper motions, and here's the result of that. And you really do eliminate the SMC quite well, and you get a very clean sample of white dwarfs. Here's another cluster we did, 6397, which doesn't have the SMC problem, but it's much less dense, much less populous cluster, as you can see, and it's also very metal poor, less likely for planets to have formed in that, I believe. So, as we've been hearing for the last, most of the day today, a few percent, something like 3% of white dwarfs in the temperature range 9 to 25,000 have infrared excesses due to dust. And here's an example of a couple of those. And the main point about this is, if you take a look at these, if they're typical examples, going out to 2 microns really doesn't do the job for you. It's very difficult to measure an infrared excess in these if you only go out to 2 microns. So you really do have to go out to 3 microns or so, or beyond that even. HST has no capability at those kind of magnitudes. And you can't do this from the ground because, as I'll show you in a moment, any kind of infrared excess that we expect around a white dwarf in 47 Tuc is going to be fainter than about 26 magnitude. And you can't do that from the ground. It's too faint. So here's, you've seen this 10 times, so I don't have to talk about it too much. Here's a simple model of the poster child for infrared excess, G29-38. Here's the data. This is the data scaled to the distance of 47 Tuc. So you get an idea of what it looks like. Those are the data. Here are some filters put on top of it. So here's F160, which is the reddest Hubble filter. And here's F150W2, which is a JWST filter. And you can see that doesn't do a very good job. Here's the infrared excess. So you really need the 3.2 micron filter to get an excess here. And this is an excess of about 1 magnitude at this kind of temperature. And for a similar white dwarf of temperature 25,000 degrees K, you can see that the excess above the black body here is fully 2 magnitudes. So this is hopefully low-lying fruit, but we will see. So here's the program which we were successful to get time on. It's an international group. Larry is the PI. We have 20.5 hours. We have the data. It came in about 6 to 8 weeks ago. There's problems with it, which I won't go into in detail, but we actually had a guide star failure also, and that data will be retaken in May. Okay, just a little bit about a probability of seeing something. If the 47 Tuck white dwarfs are like those in the field, 3% will have infrared excesses. We have about 400 white dwarfs, as you'll see, in the fields that we're looking at, so we expect a dozen infrared excesses. And if we see 0 with that number expected, the probability of that is really very small. So even if we see nothing, we know that the globular clusters are different than the field. So here's what the data, or the fields that we have that we've observed. So here's earlier observations that we did, 225 and 225 and 336, with wide field camera 3 in the core. And this is the parallel fields in 435, 555. This we're not going to probe the center of the cluster, which sits over here. Too crowded, red giants, too many red giants will just make a mess of everything. We'll get a little bit of this region over here. These were taken simultaneously, but most of our data are coming from the very deep field we did about a decade ago. There's a 120 orbit exposure in here, basically in 606 and 814. We also did with 3 out here, but we don't penetrate out this far. So this is what our fields look like, superimposed on this central core. You can see here. This is the one that we actually have a little bit of results from, which I'll show you. And this is the field that failed. So that's what they look like with respect to 47 Tuck. Okay, now from all the data that we have in 47 Tuck, we have this wonderful catalog of 1,000 or so white dwarfs in the cluster. We have various amounts of photometry, not less than 2, and up to about 4 colors. And so we can use that and fit models to it to predict what the 1.5 and 3.2 micron colors should be. So without this, we wouldn't be able to do the job because we're looking for this to be too bright, basically. And if we didn't have this information, we wouldn't be able to do the job very well. So here's some predictions of what magnitudes for this particular one should be. And these are Vega magnitudes. So we use these observed magnitudes to fit a model, and then we predict these magnitudes over here. And that's a little cutout of what these look like. So here's the first of a few pictures I'm going to show you. This is a very small fraction of a field, and these are 3 white dwarfs in the 606 field that you see, and these are the Vega magnitudes of these. This is a JWST field in 322W, 3.2 microns. These are not measured magnitudes, but these are predicted magnitudes from the process that I just showed you. And the interesting thing here, and the very exciting thing is, you see that we actually detect the white dwarfs in 3.2 microns. Doesn't mean they have an infrared excess. Fact is, I don't think any of these have an infrared excess, but the point is we can detect white dwarfs down to very faint magnitudes. And here's just a little cutout, just if you want to see more about them in the 2 colors. These are just 3 white dwarfs, and these are among the cleanest white dwarfs that we have in the cluster. That is, they're not too close to other bright stars, not a lot of scattered light. On the left is 1.5 microns, and on the right is 3.2 microns. And you can see that the white dwarfs are very nicely detected in all of these. Okay, I'm going to show you 2 images blinking on top of each other, and this is for fun and amusement. So this is an HST 606 image blinking with a 3.2 micron image from JWST. And I show this just to show you the richness of the data that you can get with JWST. Things pop out of nowhere. Galaxies pop out over here. Something comes up out over here. I don't know if there's 2 of these things. I don't know if they're stars, I'm not sure what they are, but they've come from almost invisible to incredibly bright. They both have an object there before, so I don't know what's happening, but they're incredibly bright in the infrared. There's other examples of stars. Here's one that got very bright. So you can see there's a wealth of information here, and JWST really goes quite faint to get the faint red stars. So this is all the photometry I'm going to show at this stage. This is very bad photometry. This is aperture photometry, but it'll give you some ideas. So this is in 606 and 322. You might ask, why didn't I do it in 150, 322? The 150 images we still have some issues with, but it's 606, 322, and you can see the incredible main sequence. We're down about to the brown dwarf limit here in this particular case. This is all the SMC, it hasn't been removed in this, and here's the white dwarf. So we see a clean white dwarf sequence. Now you might say, what is he saying? There's no clean white dwarf sequence there, right? Do you agree there's not a clean one? Oh yes, there is if you proper motion clean. And there it is. So here's a clean detection of just a few white dwarfs in this field, but there's no doubt we can detect the white dwarfs, and we expect to see the cluster go down to, the main sequence go down to the brown dwarf limit. So, conclusion. We've detected white dwarfs at 3.2 microns and 47 tuc, at least down to 9,000 degrees. At that temperature, we expect about a 1 magnitude infrared excess for stars that have disks. If it's 25,000, we expect 2. So the first rough aperture magnitudes that we did, the measurements look very promising. So there's a lot to come yet. And in the next few months or so, we're going to explore this in great detail. Thank you.
Maybe this is white dwarf related, but not directly. In the main sequence, you show that you can get to lower magnitudes. You can get to brown dwarf-ish.
Well, we don't know that yet. But remember, that's 606
yes.
versus 3.2. So they had to be detected in 606, which we believe went to about the end of the hydrogen burning main sequence. Right?
Okay, can those different filters be used to improve, for instance, the determination of the parameters of the cluster? Because for modeling, it's important to have well-restrained parameters, and especially for the cool ones, well, models are a little off.
Well, I mean, that we have part of our group is the San Diego group. Bergasser and his student Gerasimov, and they're working on brown dwarf models and very low mass models down the main sequence, and so we'll have that theoretical support too to see what those models look like. So hopefully this will be the first control of those kind of models at these kind of metallicities, subsolar metallicities.
Thank you.
Harvey, do you have enough filters to distinguish between a disk and a brown dwarf companion?
Yes. So because we know where the white dwarfs are, Boris.
Well, I mean, brown dwarf companions to white dwarfs. So if you detect an infrared excess to some of your white dwarfs, can you distinguish between a disk and a brown dwarf companion?
I would say the answer might be no if we don't see it. If we don't see the brown dwarf, then we won't know if it's a disk or not. But that's something to think about. I mean, we hope we can see the brown. We expect, I mean, this program was built around the brown dwarfs. I mean, that determined the exposure times. So the hope is if there are brown dwarfs there, we will actually be able to resolve them. But if they're very close, of course, the separation is very small, we'll never be able to do that. So there's potential contaminants that might mess us up. But we only expect a dozen or so. And if those dozen had a background galaxy or a brown dwarf, that would be very bad luck.
There has been searches of planets around, in globular clusters, and they haven't been very successful in getting planets in the system, basically because the environment is going to disrupt the disks and prevent possibly planet formation. This is going to be an amazing database, but do you think actually that you're not going to get truncated? By the time you get to the white dwarf, any star-star interaction is probably going to destroy everything around these stars. Have you considered?
You mean the other stars in the cluster?
Yes.
Yes. So, that's an issue. If there are disks around some of these white dwarfs, does the gravitational interaction, because it's a reasonably dense system, do they destroy them? Well, there's a few papers like that. Spurzheim had a paper that talked about, that the stars could survive disks. Remember, these disks are very small. We're talking about, tens of white dwarf radii is the size of the disk that we're talking about here.
No, but the perturber has to be farther away. That's the problem. That in order to deliver material to form a disk in a white dwarf, you have to have a perturber that is far away. And in this very dense environment, you may have problems to keep the perturber up there.
Sure, it's all possible. But I think my answer to that would be, let's look and see what happens.
Of course.
So you mentioned there should be 400 white dwarfs. I counted 14 in your claim.
No, yes, okay. That's correct. But that's one of 8, let's start. It's one of 8 fields. Okay. Remember, we have 8 fields like that. Okay, it's one of 8 fields, and it's terrible photometry, it's aperture photometry, and so we haven't gone very faint. Okay. And we've missed, if you go back and you think about this for a second, well, we'll go back here. Okay, you can see how crowded the fields are, right? So there are all those issues. And with aperture photometry, you don't do well, if you've done aperture photometry, for those theoreticians that don't know what I mean, and you just put an aperture down, measure the star, a bigger aperture down to measure the background, you subtract the two, and that gives you the magnitude of the star. That's okay if you're not very crowded, but in a field like this with a funny point spread function, it's not very good. Right?
Yeah, so you think that you'll reach
quite right.
400?
We expect an order of magnitude, several orders of magnitude more than you've seen there.
Okay, great.
I'm sorry if you already talked about this, but I'm just curious, can you remind me where the 3% comes from, that probability of finding the disks? Is it an observational constraint, or is that a probability?
No, that was well, it was largely the discussion this morning that about 3% of white dwarfs in the field have disks. Now, there's way, way more that have infrared excesses. 30 to 50% have an infrared excess. Have pollution. But the number with disks are very small, around 3%.
Okay, thank you.
I was just wondering, for cleaning the SMC with proper motion, does that mean you need HST photometry of the source in the first place, or But
I already have that.
But does it go as deep as you want for those?
Oh, no. The white dwarfs will go fainter than we'll detect for the average. The white dwarfs are very blue, generally. And with JWST, we're in much redder filters, so we won't go all the way down the white dwarf cooling sequence. So we're not going to do this with new white dwarfs. We have to know the white dwarfs to be able to do this, right? So then I know the colors and everything else.
Okay, so I think we have to move to the next speaker. Thank you very much.
Thank you.